Man, this is hard stuff. This is hard stuff. If you're struggling, you know, you got to kind of dig into what it is you're struggling with, and when you find those cavities, lacuna, is what they call it in Spanish, these gaps in your knowledge, you gotta go there. You gotta figure out what's wrong. Why do I not get this? Do I need to strengthen my unit circle understanding? Do I need fraction practice? The only way through it is through it. Okay, I want to talk about 8.2, because we didn't get to that on Thursday. And really 8.2 is just extending. We talked about sine, we talked about cosine, so now we're just going to throw all the other guys into the pot, right? Because we've got 6 trigonometric functions, right? Go ahead. Sine, cosine, what else? Tangent, which is essentially sine over cosine. What else? Cosecant. Cosecant. And who does cosecant get paired with? Sine. Nice, because everybody gets a co. So this is cosecant x. That's 1 over sine x. What else do we get? Secant. Secant, which is paired with cosine, because everybody gets a co. So secant x. That's 1 over cosine. And also, last but not least, cotangent. The ugly stepchild that we love anyways, cosine over sine, that's cotangent x. One of the weird things about trig functions is that they pop up in calculus in really odd ways as analytical tools to evaluate kind of weird integral expressions. So we're going to do a little bit of work on this. I don't know that the visualization here is as important to me as the sinusoidal stuff is, you know, but for instance, what does tan x look like? In other words, f of x equals tan x. How does this show up? Well, first of all, it's still periodic, because as we go around the unit circle, we're still going to repeat. And in fact, its period is actually half of the period of sine and cosine, because if you think about a unit circle and you think about the tangent values, which are just the y values divided by the x values, here, you know, say you have AB. Well, when you reflect it over here, you're going to have negative AB. When you reflect it down here, then you're going to have negative A, negative B. But this tangent and this tangent are the same. Because if you take the y value divided by the x value, it's B over A. This is B over A, because I got a negative divided by a negative. So basically, first of all, the period is pi, not 2 pi. Second of all, we got domain problems. How do I know, just by looking at this, that I'm going to have domain problems for tan x?
Because you can't divide by 0.
You can't divide by 0. So anytime you have a fraction with a variable in the denominator, you got potential problems. So in other words, cosine x equals 0 is a no-go. Well, when does cosine x equal 0? Let's just list out a few situations where that's going to happen.
At 0? No.
Cosine 0 is 1.
Oh, so then at 90, it's 0.
Yep, talk to me in radians.
So pi over 2, it's
That's good. Also at
That's a little too low.
So x cannot be equal to pi halves, 3 pi halves.
I'm assuming 5 pi halves and 7 pi halves. So every odd pi halves.
Get a pattern. Right, because we're adding pi, it's a periodic on pi, so we just add pi every time we get a new thing. Here, if you want to get fancy, pi halves plus or minus pi. N pi, where n is an integer. Woo! Let me clean this up. X should not be equal to pi halves plus or minus n pi, where n is an integer. This is the symbolic way to say every single domain problem in one sentence. Okay, fun. We're doing great. Life is good. We know that the period is pi. We know we got domain problems. What happens when we approach the domain? This is a nice little preview of some calculus thinking. So, what do I mean? We know that at pi halves, we got some kind of problem going on. As we approach pi halves from the left and the right, what happens to the value of tan? Let's take a look. First of all, we're going to need to decimalize this. Pi halves is about 1.57 something, right? Give me one more digit. 0.5707. So 1.571, right? So let's approach that from both sides. We'll say, let's make our inputs. Am I still on the board? Yeah. X. How about 1.56? How about 1.57? How about 1.5705? That should get us pretty close. That's coming in from the left side, coming closer and closer to my problem spot. So what I want you to do is just put those numbers in to tan. Tan 1.56, tan 1.57, tan 1.5705. Tell me what happens to the output. Sure you're in the right mode. I got 92.6. I got 1,255.8.
The numbers are going up exponentially, like to infinity.
A lot. When they're getting big fast. Now, what about this left side? Let me get some numbers. 1.58, then 1.571, and 1.5708. I want to stay on the right side of pi halves. Getting smaller, getting closer to pi halves. 272,000. Jeez. Okay. Negative, and it's getting more negative. Here's what that looks like. We have a vertical asymptote. As we approach it from the right side, our numbers blow up. As we approach it from the left side, our numbers blow up, but in the negative direction. And that actually is pretty much all we need to know about tangent, because if we put those two pieces together, at some point it goes through zero, which actually happens at zero. So I get these little, I don't know what you call them, flattened out S shapes or something. Repeated over and over again. As you bump up against the asymptote on the right side, it goes to infinity. As you bump up against the asymptote on the left side, it goes to negative infinity. Let's take a look at Desmos' rendering of that. Let's see it in action. How fun would it be to do transformations on tan? I don't know, not that fun. I can think of more fun things. But, you know, we can do tan of 3x and 2 tan x. Shifts up, down. Tan's a pretty weird guy. Okay. Let's analyze another one. Cosec. What does cosecant x look like? Well, I'm just going to venture that the period is 2 pi. I might be wrong. Well, let's start with the assumption that it's 2 pi because it's based on sine x and the period of sine is 2 pi. What about these domain problems? Got domain issues?
If it's 0, you can't have 0.
So
Wait.
Make the statement.
So it's all real numbers except for when, or domain is all numbers except for when.
Yeah, I wouldn't jump to telling me where the domain problems are. I would start with this condition that's going to tell me where they are. So I don't want the denominator to be 0. Make that a sentence. Not about x. We got to do some math to think about that. But what would the statement be?
You lost me. I don't, wait, what?
Like, this is a common problem with domain analysis. If I have this problem, you're not going to leap to telling me what x values are not in the domain. You know there are domain problems, but where you should start is just saying, hey, 3x squared minus 4 had better not be equal to 0 or I'm going to have problems. This is where. So where am I going to start here with my domain problems?
Can you just say 1 over sine x is not equal to 0?
No, because I want the denominator not to be 0. I don't care about the whole thing. What's the denominator?
Sine x?
Sine x. Sine x had better not be equal to 0. This is where I mean.
Is that fair to say if we're talking about cosecant then? Can you say if we're talking about cosecant then sine x better not be 0? Is that fair, or is it because those? I mean, they're
Just-
related, but
I'm having a hard time putting the words together.
well, I mean, so it's like, is that a fair statement to, I mean, you were talking about cosecant, but you're using the definition of of sine when you're talking about cosecant, right? Because you said sine x is not 0, but we're talking about cosecant.
Right, because I know that cosecant is 1 over sine x. So
Well, that's
where are
right.
the domain problems are when sine x is equal to 0. So if I want to answer the question, I'm going to start with this statement.
So
When
that's a fair statement to say. Okay, great.
so sine x not equal to 0, now we can try to step forward. Just give me one solution that would make this a problem, and I'll put a not equals instead of an equals. When the sine equals 0.
At 0.
At 0. You start at 0. X had better not be equal to 0. Or 2 pi, but also and 2 pi and 3 pi. So, anybody want to try to generalize with n? Right, that's hard. N pi, where plus or minus n pi. Look, if n is an integer, it doesn't have to be plus or minus, where n is an integer. Okay. This is making me think that the period might actually be pi, not 2 pi, because it seems to be repeating every pi. So let's take a look. So again, when I bump up to those domain problems, I'm going to be shooting off to infinity. You think about why that happens, right? If you take 1 and divide it by 0.1, 1 divided by 0.01, 1 divided by 0.001, what's happening here is dividing by smaller and smaller numbers. Oops, sorry. This is actually where you start calculus. If you take 1 divided by n, and you let n get closer and closer to 0, what happens is this number is going to blow up. You can just do it yourself to see what happens as this number gets smaller and smaller. The result gets bigger and bigger. So I have these places where I'm shooting off to infinity. All right, I'm going to try and problem. So I know that at 0, at pi, at 2 pi, shooting off to infinity there. Here we're shooting off to negative infinity. Why? Because this is the bottom side of the graph where the sign values are negative.
It's a little low again.
0, pi, 2 pi. On this side, I'm shooting off to infinity. On this side, I'm shooting off to negative infinity.
And that information you only found out just by plugging in numbers, right? Was there like a logical information behind that?
Behind which part?
The going off into infinity. Like I see this in getting closer and closer to infinity, but this is just, was there a logic behind that? That was just, I'm plugging in numbers as they go in the sequence.
Yeah, well, I'm looking at it numerically for your sake, but where you would head and this is where you start in calculus, you start thinking about limits. What happens as I push this number, my input, closer and closer to pi? What happens as I do that from the left side? What happens as I do it from the right side? And you can see it numerically happening. Logically speaking, that's what I was trying to get at here. And again, I'm using numbers to explain it.
Yes.
As you divide by smaller and smaller numbers, closer and closer to zero, it has an impact in making this fraction larger and larger.
Here, yes. And so my question was essentially, you're doing it by point by point by point. Is there an easier way other than just taking the limit of it and knowing that?
No, I don't think so.
Okay, sweet. Okay, thank you.
Now, what happens in the middle of these two little infinite things? Well, let's think about on this side. Here's sine. As we got closer to zero, this blew up. Zero blows up. Zero from the negative side goes off to negative infinity. But what about here? This is at pi halves, which for sine represents a maximum. And what is the output at pi halves? Sine pi halves. 1. 1/1 equals, so it's the same for cosecant. So there's this minimum that you drop down to, so you get these little U shapes. Same thing here, except it's the max. Gets up to -1 and then it goes all the way back down to negative infinity. Let's take a look at sine and cosine put together. Sorry, sine and cosecant put together. So we got sine x share. I'm going to put in the asymptotes. I'll put in one asymptote. X equals pi. Okay, so the red are the cosecant. The period is 2 pi, because in order to really repeat itself, we have to go a full 2 pi to get back to the upward u.